Everybody, this is Dr. Nigro with the Physics Fundamentals Screencast. This is in our projectile motion unit, and we're going to be looking specifically at horizontal projectiles. All right, so remember, projectile motion we've defined before is a motion that has two dimensions to it, an upward and outward portions occurring simultaneously. And from our earlier videos, we have learned that we have to keep those types of motion, those components of our motion, separate when we do our calculations. Horizontal projectiles are a special type of projectile motion. All right, so for these, we have something sitting up on top of a cliff here. I'm going to make a cannon. All right, and that cannon is going to shoot an object with all horizontal motion. All right, now we know that it's all horizontal initially because of the way the cannon is pointed. So it's all horizontal. Initially. All right, and that's a key word, initially. All right, so that means the angle of theta here is going to be 0 degrees. All right, and if it's all horizontal initially, then our vertical velocity is initially 0. Okay, now we know that the ball doesn't follow this path. It actually begins to bend down towards the earth. All right, and that's all due to gravity. All right, so while we may initially have 0 vertical velocity, we do add vertical velocity in. All right, so if we put together our organizational chart, our change in position, our velocity values, acceleration, time, and then any resultant and theta information. All right, if it's a horizontal launch problem, we can actually add in one additional number from the other ones we have before. So we have our horizontal and vertical columns. We stop at time because they share time. All right, we know that the horizontal motion is constant, so the acceleration horizontally is 0. And we know that the vertical motion is changing because of gravity, so we get an acceleration rate of negative 10 meters per second. Now, because that vertical motion is changing, there's going to be an initial and final velocity, and here's where we can add in one more number. All right, we know if it's a horizontal launch problem, that initial vertical velocity is also 0. All right, so that's really handy when we work these problems. Now, I'm going to copy this because then we don't have to write it again. All right, so let's try a problem. Okay, so we've got a ball rolling with a velocity of 2.5 meters per second off the edge of a 1.8 meter high table. All right, so I'm going to start by filling in what I know. All right, so I know that it's a 1.8 meter high table, so that's going to be my vertical distance, or the change of position vertically. All right, I know initially we've got a velocity of 0 vertically, and I know acceleration is affecting its motion. All right, I don't know very much on the horizontal side except for the velocity at which it is rolling. All right, so it's rolling at that velocity, which means that when it leaves the table, that is its initial horizontal velocity, and because that's constant, it stays at that value. All right, now, first problem. How long is the ball in the air? Now, on our earlier screencast, we were using the horizontal motion to find that because we knew the change of position and the velocity, although I see I put my velocity value in the wrong spot. Let me fix that. It should be 2.5 meters per second here. All right, this time though, we don't have enough information horizontally, but we do have enough vertically. So this time we're going to be using our vertical information to find the time. All right, so we know that time is equal to final velocity minus initial divided by the acceleration. We have those three values. No, we don't. No, we can't use that formula because we don't know V final. All right, my bad. Let's try again. I know. Change in position equals the initial velocity times time plus 1/2 acceleration times time squared. All right, this is going to work because our initial velocity is 0, so that's going to go away. I know my change in position is 1.8 meters, but it's negative because that ball is moving, or cannonball is moving downward. All right, I also know that my acceleration is negative 10 meters per second squared, and that leaves me one unknown, time. All right, so I plug everything in and solve for t, taking a square root at the end, and I find that the ball is in the air for 0.6 seconds. All right, so we'll put that over here in our table. All right, now it wants to know, well, how far away from the table does the ball land? All right, so we're looking for the range. This is the change of position horizontally. And now that I know the time, I have my horizontal velocity. I can solve for that change in position. So the change in position for x is going to be equal to my horizontal velocity times time. All right, so change in position equals 2.5 meters per second times 0.6 seconds. So the change in position horizontally is going to be 1.5 meters. All right, so that could go in here too. Okay, what is the vertical velocity of the ball just before it hits the ground? All right, so we're looking for V final this time. All right, and I have a formula. V final equals V initial plus, sorry, let me fix that. V final equals V initial plus acceleration times time. All right, so our final velocity is equal to 0 plus negative 10 meters per second squared times our time of 0.6 seconds. So the final velocity vertically as the ball hits the ground is negative 6 meters per second. All right, so that goes here. All right, what is the resultant velocity, magnitude, and direction of the ball just as it rolls off the table? All right, so here's an important word. We're up at the beginning of this motion. All right, so in that case, there is no, so I know that the horizontal velocity is all there is. The vertical velocity is 0, and the horizontal is 2.5 meters per second. So I could plug that in to Pythagorean's theorem, but I would get back that our resultant velocity is equal to the x component, so 2.5 meters per second. And because it's rolling off the table, right, it has an initial theta angle of 0 degrees, right, or you could say pointed east. Okay, so you don't really need to do any calculations, but you do need to think about what's going on at the beginning. All right, now it wants to know, well, then what is the resultant velocity, magnitude, and direction of the ball just before it hits the ground? All right, so if we think about that ball coming down towards the ground, right, it's going to have some set of x and y components and then some angle theta. All right, well, we've calculated Vy and we know Vx already. Vx is 2.5 meters per second, and the final vertical velocity is negative 6 meters per second. All right, so with that, we can use Pythagorean's theorem. So we plug it in. We know it's the horizontal velocity squared plus the vertical velocity squared. And that is 2.5 meters per second squared plus negative 6 meters per second squared. Plug it all in, solve, and we find that the magnitude of our velocity value here is 6.5 meters per second. All right, but we also need to know the angle. All right, so we need to calculate theta, and we're going to do that using our inverse tangent. So theta is the inverse tangent of our vertical velocity divided by our horizontal. So we plug those values in. Remember to keep your negative sign for that vertical velocity. So negative 6 meters per second divided by 2.5 meters per second. Take the inverse tangent, and we find that our angle here is negative 67.4 degrees. All right, so our resultant velocity is 6.5 meters per second at 67.4 degrees south of east. So that's our velocity right before the ball hits the ground. Okay. All right. Let's try another one. All right. This one's a little bit different. Let's see what we got here. A cannonball is fired horizontally off a cliff. All right. So it's a cliff problem. And the cannonball is in the air for 8.3 seconds and lands 1,455 meters away from the base of the cliff. All right. So let's look at what's happening here in terms of the motion. All right, we basically have a cannonball. Whoops, sorry about that. Cannonball that's being fired horizontally. All right, and we know how long it's in the air, and we know how far away it lands. All right, so let's fill in our table here. All right, we know how far away it lands, so that is our horizontal change in position. And we know the time that it's in the air, 8.3 seconds. Okay, so the first question is, what is the initial horizontal velocity? All right, so we know the change in position and the time. All right, so the velocity horizontally is going to be equal to that change in position divided by time. All right, so Yes, we're going to have 1,455 meters divided by 8.3 seconds. So its initial horizontal velocity is 175.3 meters per second. All right, so 175.3, sorry. Okay, next, how high is the cliff? All right, so this time we are going to be looking for our vertical change in position. All right, so if I look at what I know time, I have acceleration, and I know the initial velocity is 0. All right, so with that information, I'm going to use my delta y formula that includes those variables. All right, so change in position equals v initial times time plus 1/2 at squared. All right, because the initial velocity is 0, this piece goes away. So the change in position is going to be equal to 1/2 of negative 10 meters per second squared times 8.3 seconds squared. All right, so we plug all that in, and we find that the change in position is negative 344 meters. All right, so that's the cliff is 344 meters high. The negative sign just tells us that the cannonball is moving downward. Okay, what is the resultant velocity of the cannonball just as it leaves the cannon? All right, so this is similar to what we saw in the last problem. All right, we know that the horizontal velocity here is 175.3 meters per second, and we know that the initial vertical velocity is 0. So what that tells me is that the resultant velocity is all horizontal, so 175.3 meters per second, and it's being fired horizontally. All right, so that means a theta of 0, or you could just say, whoops, not east. Okay, last one. Now, what's the resultant just before it hits the ground? All right, so we need V final vertically. We need this number right here before we can calculate this. So that's going to be our first job. So calculate Vy final. All right, that's pretty straightforward with the information that we have. We'll have V final equals V initial plus acceleration times time. So final velocity equals 0 plus negative 10 meters per second squared times 8.3 seconds. So our final velocity right before it hits the ground vertically, put some lines in here, is negative 83 meters per second. The negative sign again telling us that the object is moving downward. So negative 83 meters per second. Okay, so that's the first part. All right, now to calculate the resultant. All right, so we're going to use our formula, Pythagorean's theorem, all right, the horizontal velocity squared plus the vertical velocity squared. So V sub r is going to be equal to 175.3 meters per second squared plus negative 83 meters per second squared. Plug that into our calculator, and we have a magnitude here of 154.4 meters per second. All right, but that's not enough. We know that velocity is a vector quantity, so we need the direction or the angle, theta. So we'll use our inverse tangent formula, which is the vertical velocity divided by the horizontal. So in this case, negative 83 meters per second divided by 175.3 meters per second. We plug that in and we find that our angle theta is equal to negative 25.3 degrees. So our resultant is 154.4 meters per second at 25.3 degrees south of east. Okay, all right, so those are just two different examples of a horizontal launch problem. Sometimes I call these cliff problems because they're usually fired from a cliff. All right, but it could be anything. It could be something rolling off a table. It could be, I don't know, somebody rolling off a diving board. It's just something where the initial velocity is all horizontal, that there's no up or down initially. It's all out. Okay?